Problem 2. Mean of 50, standard deviation 10. Mean of 50, standard deviation 10, and I need to find greater than 54. So I am greater than 54. So it's going to be 54 minus 50 over 10. Our sample size is 25. So that's 4 over 10 over 5 is 4 over 2 is 2. So I need to find the problem greater than 2. Here's 0. Probability greater than 2. Here's 2. And I want this little shaded piece in the tail here. So I got to find that. I got to find that from the table. Go find 2 and find tail. Tail is 0.0228 here. So this p-value 0.0228. So let's look at the next one. What's the probability sample mean is less than 47? Less than 47. So this is going to be sample mean M less than 47. Same setup here. Mean is 50. Standard deviation is 10. So this is the same formula. Less than 47. 47 minus 50 over 10. Over square root of 25 because our n is 25 here. Negative 3 over 10 over 5 is negative 3 halves. Negative 1.5, and I want less than 1.5. Whoops, horrible distribution here. I want this tail here. So I want the tail in the table again. Go find the table. Find 1.5. Tail is 0.0668. So this tail here is 0.0668. You're done. Okay, so let's go to another one. I don't want documents. I just want a blank, and I can't figure it out for this thing. Okay, so let's. I'll just keep adding whiteboards. There should be a way to just extend it, but I can't figure it out based on this. Let's go to the next problem. So I want part C between 2 points. So I want between 48 and 52. So I need Once again, we know that the mean is 50. We know that sigma is 10. We know that n is 25. And I want between 48 and 52. So I want the boundary there. I want between those two. So this is what I want. That's supposed to be symmetrical, obviously. I'm not drawing it well. So whatever the z value is here, that corresponds to 48. And whatever the z value here, that corresponds to 52. I want that region here. What are these probabilities here? So I need to find those z values first, and then I need to convert them in the table. So let's look at that. How do I get the z value? Well, I have that same formula that we've been using, m minus mu over sigma divided by square root of n. That's what we'll be doing this whole problem too. So put it in. This is 10 over square root of 25. This is going to be negative 2 over 10 over 5. Negative 2 over 2. Negative 1. And we also have this one. 52 minus 50 over 10 over square root of 25. That's going to be 2 over 10 over 5. That's going to be 2 over 2, positive 1. So this is a negative 1. And this is z is positive 1, right? So I want between negative 1 and positive 1. Go to the table. Find negative 1. Find 1, because there's no negative. So we want mean to z. So 0.3413 is for negative 1. But it's also the same for positive 1. So 0.3413 for negative 1, 0.3413 for positive 1. And we have that. This is 0.3413. And we have, so 0.3413. And we add them together, and our p-value is 0.6826. So the probability is 0.6826 that we find scores between the values of 48 and 52. And that's done. Let's do another one. So problem 3. Researchers claim herbal supplements such as ginkgo, biloba, or ginseng changes human memory. How do we test this? We have 36 students. We know that there's a normal distribution with a mean of 80, standard deviation of 18. So let's write all that down. Mean of 80, standard deviation of 18. So we know sigma, so we know it's going to be z. We know the sample size is 36. It's one sample, so it's going to be one sample z. What else do we need? We know the mean of the sample is 85, and we're using 0.05. Now we have to know if that's directional or not. So the mean is 85, and we're using we're using alpha is 0.05. Now, the reason why it's not directional is because we use the word changes. Right? Changes. Ginkgo biloba changes human memory. That's not indicating a direction, so therefore it's non-directional. It's two-tailed. So let's do the null and the alternative. Null. Herbal supplements like ginkgo biloba. I want to write herbal supplements. Have no effect on memory. And the alternative, herbal supplements change memory. Okay. So we're testing those hypotheses. Let's calculate our z. We know that z is equal to m minus mu, the one sample, over sigma, which we have, over square root of n. We know that our mean is 85 of this sample. We know the population mean, which represents the null hypothesis, is 80. We know sigma is 18, and we know the square root of n is going to be square root of 36. So it's 5 on top. 18 over 6 becomes 5 over 3, becomes 1.67. And then we need everything, we need the critical value actually. So here is 0, here is 1.67. We need the value in the tail. So we need to find the critical value that corresponds to this situation here. So remember, for the table of critical values for z, this is two-tailed, and this is at the alpha of 0.05. So we know the critical value from that table, the 4 critical values I gave you, is plus and minus 1.96. So that's our critical. We also have a negative 1.96, but we're not really going to look there. Our value is not more extreme than the critical value. See, 1.67 is not more extreme than the critical value of 1.96, so therefore we failed to reject the null. And you're done. Failed to reject the null. Let's do problem 4. Sample of 9, sample of 9 is a mean of 26, standard sum of squares of 128. Sigma is unknown. So right there, sigma is unknown. We know it's not z, we know it's t, because sigma is unknown. 95% confidence interval. Let's do it. So our n is 9. Sigma is not known. We know the mean, the sample mean, obviously, has to be given to us, and it's 26, and the standard sum of squares is 128. 26, 128. Sum of squares is 128. We also know that to calculate the variance, which we need here for the confidence interval, we know that s squared, the variance, is equal to sum of squares over degrees of freedom, which in this case is equal to 128 over 8, because degrees of freedom here is n minus 1, because it's a one sample test. So 128 over 8 is going to be 16. So we know if the s squared is 16, then s is the square root of 16, which is 4. So our standard deviation is 4. We also know that the confidence interval for 95%, this is 95%, I believe, 95%, is equal to the mean of the sample, m, plus and minus the critical t value with an asterisk here. This represents 0.05 two-tailed. And the reason it's 0.05 two-tailed is we have a 95% confidence interval. So if I do 1 minus 95, I get 5.05, right? That's why it's 0.05 two-tailed. Confidence interval is always two-tailed critical value. Always a two-tailed critical value. If our confidence interval was 90, then we look at the t of 0.10 two-tailed. If our confidence interval was 80, we look up the t of 0.20 two-tailed. So this confidence interval and this t value, critical value, have to add up to 1, basically. 95 and 5 add up to 1, or 100. So that's how we do this. We get that from the table. And this value is going to be times the standard error, which is s over square root of n. So plugging in here, my mean is 26, so CI 95 is equal to 26 plus or minus this critical value, which I have to find from the table. So we're going to go back to the table again. And we're going to find 0.05. Got to go to T, though. 0.05 two-tailed right here. Degrees of freedom is 8. So we get 2.306. 2.306. That value is always positive for the, since we're doing two-tailed, this value is always going to be positive for the confidence interval. 2.306 times S, which is 4, over the square root of n, which is 9, so square root of 9. This gives me 26 plus or minus. Now I have to compute that, so I'm going to use R to do that. You can use your calculator. I'm going to use R. R is timing out on me again. R is kind of like my calculator. It's very easy to use. You can just type in the, you don't have to really know what you're doing here. You just type in what you're doing, but your computations here. So it's 4 over 3 times 0.2306. So 2.306 times 4/3, right? Because that's what it's going to be. 3.075. Because this is really .306 times, this is 4 over 3, so it's 1.33, repeating, so it's 26 plus or minus that value, which I have here under R, right? So 2.306 times, I'll put 1.33 in, and you get the same answer within rounding difference. It's 3.07. I rounded 3.06. It's really the same thing. We'll use this one as more precise. 3.075. You might get a little bit because of rounding error. So what is that? 26 plus 3.075. Put it in again. 26, we'll do the minus first. And then 26 plus 3.075, that's easier to figure out. So we're at 22.925. You might have some rounding error here. 22.925, that's the lower value. And the upper value is going to be 29.075. Such a lower and upper value. Done. Okay, so that's problem 4. And now we got to do problem 5. So in problem 5, we have 2 samples, and we're seeing if exercise leads to better strength and balance in the elderly. And these are our 2 samples. So our null is exercise does not improve strength balance. And our alternative, let's see if it's one-tailed or two-tailed. We're looking at changing. So it's saying changing strength and balance. That's two-tailed. We're not indicating a direction, so it's non-directional. So exercise changes strength and balance in the elderly. This is in elderly. I should put that up there. I'm just trying not to write too much on this tablet because I write very sloppy on the tablet. So now let's calculate the t. First, we need the pooled variance. These are independent groups. Let me get rid of that. These are independent groups, so I need to find s squared sub p, the pooled variance, which is sum of squares 1 plus sum of squares 2 over degrees of freedom 1 plus degrees of freedom 2. And the reason it's independent groups t-test is 1, the population variance is not known, and there are 2 samples and there's different people in each sample. So that's why it's independent groups t. And we also need to do the s squared sub p. We need to do the t value, the t formula, which is mean of the first group minus mean of the second group, all over square root s squared sub p over n1 plus s squared sub p over n2. So let's find those means. We have them. The mean of the first group is 10 and exercise is 14. So I'm going to do exercises group 1 and the controllers group 2 because I like positive numbers better. So 14 minus 10 here. It doesn't matter which way you do it because it's two-tailed. 14 minus 10 over the pooled variance. So we got to do this first. Let's go find our sum of squares. Sum of squares of 1, 72, and 88. So this is 72 plus 88. And then degrees of freedom of the two are 10 and 8. Degrees of freedom is 9 because it's n minus 1. So degrees of freedom of group 1 is 9. Group 2 is 7. So, and it doesn't matter which way we write this. We could write 7 and 9. We could write 88 plus 72. It doesn't matter which group is first or which group is second because it's pooled. So this gives me 160. This gives me 16. My pooled variance is 10. So this becomes 10 over n1, which in this case it doesn't matter which group it is. So 10 over n1, which this is n1 exercise, so it's 9. So this is 10 over 9 plus 10 over 7. So this becomes 4, and this is the square root of 10 over 9 and 10 over 7. Oh, actually n, I'm sorry. I'm putting degrees of freedom. I should be putting n in here. Whoops. These are not degrees of freedom. This is n. So this is 10 over 10 plus 10 over 8. You got to use the n's down here and not the degrees of freedom. Make sure you do that right. So this is square root of 1. 10 over 8 is going to be 1 1/4. So this is 4 over square root of 2.25. This is 4 over, that becomes 1.5. So 4 over 1.5. What's it going to be? 4 over 1.5. 2.67. So now we have to find the critical value for that. So T crit from the table, we want 0.01 this time. We're testing at a 0.01 two-tailed from T. So 0.01 two-tailed is going to be a very high number. Find the 0.01 here in the table for two-tailed. Our degrees of freedom is n1 plus n2 minus 2, which is 16. So we have 16 degrees of freedom here. And I get 2.921. Plus or minus, because it's two-tailed. Plus or minus 2.921. There's our... Here's 0, right? Here, all the way out in the tail is 2.67. But our critical value is even further away. And it's also down here, by the way, because it's two-tailed. Since our obtained value is not more extreme than our critical value, we fail to reject the null. So we conclude that there's no evidence that that exercise works to change strength and balance in the elderly. Failed to reject a no. Exercise does not change uh, strength and balance in the elderly. Actually, I like the word change better. I shouldn't put improve here. I should put does not change, because that's kind of because we're doing two-tail here. Exercise does not change strength and balance in the elderly. Exercise changes strength and balance in the elderly. Okay, and that's it. Problem 5 is done. So hopefully that helps. And study hard. If you have any questions, let me know. Send me an email. Bye for now.